Welcome everyone to the final side event for Phi-week. This is on machine learning for operational sea ice charting. It's the second in our ongoing series. We also had a side event last year at Phiweek. So it's great to see some of the presenters from last year back to tell us the advances they've made. And I think even more exciting is that we actually have about half the people are new to this group. So it's exciting to see that the community is growing. We are very tight on time. In fact, what happened was originally this was going to be a 2-hour session, and we received a lot of excellent submissions, and we requested, and Isa kindly agreed to extend the session to 3 hours. But even then, it's going to be tight, and poor Gordon Davidson is last speaker, so I want to make sure he has time. So we will be quite strict about time limits. Hopefully people will take no more than 10 minutes for the presentation, and I will be giving a warning with 1 minute left. We'll see how we do with times for questions. Please put any questions you have into the chat window, and we'll try to get at least one question in per speaker. We have a break scheduled about halfway through for 10 minutes. Hopefully we'll also be able to have that full break, because I know 3 hours is a long time. So I've got the first talk. I've got the shortest talk, so I will try to do that on time. All I want to do is just briefly mention that one of the outcomes from all of this work will be a machine learning for operational sea ice charting challenge, which is being offered in collaboration with Philab. We have a project to implement this, which also includes creating a new and improved training data set. As part of the challenge, we'll also be providing access to machine learning resources for those who want them, and hopefully facilitating communication and collaboration within the community over the coming year or so. In that collaboration, there'll be some workshops where we will be looking at the results from the competition, and as a community, hopefully talking about what's working, what's not, and where we should go in the future. The training, there is a current training data set which is available in the machine learning platform, which I'll talk about in 1 second. That set will be expanded to cover more geographic areas, include more recent data, and importantly, add in ambient information in addition to the usual star images and ice charts. I mentioned that there'll be a platform available. This is the machine learning platform associated with PolarTep. It provides, in addition to compute resources, GPUs, it provides tools for the complete life cycle of your data and your the output from your training, etc. There's a link there. I'll put it in the chat window as well. Feel free to go in and sign up now and start kicking the tires. You're not required to use this platform. It's just here if you want to use it. And finally, the competition, the actual parameters of how the competition will run have yet to be completely finalized, but the idea is that you will use this new training data set, and you'll be asked to do something along the lines of retrieving sea ice concentration, stage of development, and flow size. There will be a jury that will assess the submissions. That jury will include representation from the International Ice Charting Working Group, So we want to make this, the results from this competition, something that the operational CI services are aware of, and have a dialogue with them about how the results meet their needs. So that's it for me. I think I'm on time. First speaker will be Jorgen from DMI, and he will talk about the ASIP data set that is the precursor to the training data set we'll use in the competition. Are you unmuted?
Can you hear me now?
Yes.
Then I'll start sharing. Just a second. So, and you can all see my screen, I guess. So yes, my name is Jørgen Buus Hinkler. I'm from the Danish Meteorological Institute. I will use the next 5 minutes to provide a little additional information on the data set that David had already mentioned. Well, I will provide the information now that also, as David did, that there's a new AI for Arctic training data set under construction. That's what will be provided for the challenge. But as already mentioned, it's not yet finished, but that will be done during the next couple of months or so, or something like that, maybe a little more. So what I will do now is discuss a little bit what we already have and what is going to be new and additional. What we already have in our existing dataset is 461 files in NetCDF format. And the temporal coverage of these files are from May 2018 till March 2018 and until May 2019. And these data files provide synthetic aperture radar from Sentinel-1, which is the sort of the main input data source, but all the data is sort of used for training against the reference of sea ice charts. So what you see to the left is the coverage, the spatial coverage of all the Sentinel-1 satellite scenes, which are matched up or co-located with the ice charts covering the same areas as the satellite scenes. In addition to the SAR data, we also provide microwave radiometer measurements from the AMSA-2 sensor at the JAXA satellite, and all SAR data are corrected and calibrated with the ESA noise correction algorithm, and also noise correction algorithms developed by the Nansen Center. So there's basically 2 different versions of these SAR data. To get a better visual presentation of what it's all about, so we can see here now, we have 2 examples of the SAR data. These are the HH and HV polarizations of Sentinel-1 imagery. And in addition to that, which I forgot to mention in the first place, that we are also providing a distance mask or distance layer, so to speak, because we've figured out that the distance to land may play an important role in for the deep neural networks in the learning process of the neural networks to learn about the ice features. And as I mentioned, yes, the ice charts provide the reference data and the spatial temporal coverage is basically Greenland, the Greenland waters during the period from 2018 to 2019. So the question is then now, what will be new? What is the next data set gonna contain in addition to the data we already have for Greenland? In addition, we will also provide wind data from the reanalysis data from the ECMWF, and there will be some sort of sea surface temperatures as well. And all that, yes. Any?
No, continue. Just
okay.
give me a time check.
Okay, there's 1 minute left. All these data will be co-located with a larger data set of ice charts. We will attempt to include data from both the Norwegian Ice Service and the Canadian Ice Service and the existing ice chart set of data of ice charts that we have from Greenland, plus all data available from after 2019 and until we attempt to include all of 2021 as well. And in addition to that, we will also provide the high resolution SAR scenes from the IV mode, and everything will be provided in dual polarization. I think that's what I have to say, Annie. So questions are welcome.
Okay, we're going to, there's some questions here which we'll come to, but first we're going to go on to Andreas, who will talk about their work using this data.
Yeah. Can you stop the sharing maybe? Maybe I can. Okay, sure. Yeah, so my name is Andreas Stockholm. I'm doing this talk or this presentation together with Thor. Are you able to unmute yourself, Thor?
There we go.
Okay, great. The floor is yours, Thor. You
Sure, yeah.
Start.
Well, my name is Thor Wulff, and I will be giving a brief presentation on the state of our development of deep learning models for automated sea ice charting in support of the ice service at DMI. And specifically, we use convolutional neural networks to fuse satellite SAR and passive microwave radiometer observations in order to generate maps of the sea ice conditions in the Greenland waters. Of course, before I begin, I would like to acknowledge all of the good people and my co-workers and other partners that have contributed to this work. So yeah, you can, next slide, yeah. All right, so Jørn already went over the data set in his presentation, so I'll not linger too long on this slide. Just saying that we use the AI for Arctic Sea Ice dataset version 2 to train our operational model at DMI. The model takes as input the Sentinel-1 and the AMSA-2 observations, and as the target data, we use the sea ice charts produced by the DMI ice service. And these sea ice charts contain information about the total sea ice concentration, as well as partial concentrations of the sea ice stage of development and the sea ice form. And in this presentation, we will be focusing mainly on the total sea ice concentration. Next slide, please. So the main advantage of the SAR data is the very high spatial resolution, which allows for a quite detailed mapping of the sea ice conditions. But the SAR data also has the disadvantage that it contains several ambiguities in the microwave signatures of sea ice and open water. The SAR backscatter behavior is in large part determined by the surface roughness, and some sea ice types, such as fast ice, can develop very smooth surfaces, which might be misinterpreted as a smooth ocean surface by the machine learning algorithm. So for this reason, we also include the AMSA-2 data as input to the network, since in the AMSA-2 data, it is fairly it is fairly easy to distinguish areas of sea ice and areas of open water. And therefore, this data can be used to resolve some of the ambiguities that are present in the SAR data. Next slide, please. And in this particular scene from the Scoresbysund fjord in East Greenland, we have landfast ice within the fjord system, which can be difficult to spot in the SAR data. So here in the bottom row, we compare a model trained on only Sentinel-1 data and a model trained on both Sentinel-1 data and AMSA2 data. In the bottom left corner, we see the sea ice concentrations assigned by an ice analyst at DMI. And in the middle, we see the prediction made by the Sentinel-1 only model. And on the right, we see the prediction made by the Sentinel-1 plus AMSA2 model. And as you can see, the Sentinel-1 model falsely predicts open water within the fjord system, whereas the Sentinel-1 plus AMSA2 model correctly classifies the sea ice within the fjord. So in cases such as this one, with the SAR data being ambiguous, we rely quite heavily on the AMSA2 data to resolve these ambiguities. Next slide. All right, so let's take a quick look at our model architecture. Our model is a multitasking, fully convolutional neural network that performs pixel-wise classification. It consists of a backbone network and 3 head networks. The backbone network consists of 6 stages that extract features at different spatial scales. And these multi-scale features are fed to the 3 head modules, each of which has its own target data, which is the total sea ice concentration, the sea ice stage of development, and the sea ice form. So even though we are currently only using the model to predict sea ice concentration in our operational chain at DMI, we use the 3 heads in order to utilize all the information available in the sea ice charts during the training of the model. And the reason we do this is that we have found that sharing the backbone across these 3 objectives improves the performance on each individual objective. And this is likely due to the tasks being very related, and the synergetic information is being shared between them during the training of the model. And also, eventually, we would like to have an operational system that is able to estimate all the information that is available in a typical ice chart. And therefore, we have to consider the compute requirements of such a system. And in this regard, it is much more efficient to run a multitasking network where the backbone is shared between the objectives than having to run multiple individual networks. Next slide. We have a test data set consisting of 20 handpicked scenes, and in this figure here on the left, we have some results from running the model on this test data set. Here we've plotted the sea ice concentration predictions made by the model against the sea ice concentrations assigned by the ice analyst at the DMI ice service. And as you can see, there is a decent level of agreement between the model and the ice analysts. We achieve an R² score of almost 90%. Indicating that the model is quite accurate in its estimation of sea ice concentration. And we are currently using this model in an operational setup at DMI, where we continuously generate and update mosaics, such as the one on the right side of the slide here. And this automatic product is pushed to the DMI ice service in a format that can be directly integrated into their GIS software in order to assist them in their daily production of ice charts. And these mosaics are also pushed to the website, which is linked here at the top if you want to have a look for yourself. That was it for me. So over to you, Andreas.
Thank you, Thor. I will also talk a little bit about going in line with the segmentation of recreation of sea ice charts, but I'll take a little bit of a step back and only use synthetic aperture radar, or SAR, and discuss some of the issues that are occurring here. And to that extent, I have another scene from the western parts of Greenland, which contain a lot of sea ice, as you can see here. And I'm using a typical unit for this task. And for this particular scene, we have some issues in the upper left corner where the model thinks is close to open water, but in reality, it's fully packed sea ice cover. And the fusion between SAR and passive microradiometry does solve this. However, it does also mean that we are dependent on multiple satellites. So I'm trying to investigate if we can overcome some of the difficulties of doing SAR modeling by itself. Yeah. So the first thing we're investigating here is the receptive field of the network, and that's how many pixels a network is capable of seeing. So these SAR scenes are really huge. And if we take a look at the area up here, we can see that the red square here is what the model is capable of seeing. And this is very difficult to distinguish anything. The second issue is the SAR noise. So that is usually quite present in the HV SAR polarization, where we get these long vertical lines in the image. And if we take a look at zoom in, we can see we have this very significant transition between these two subswaths in the Sentinel-1 image. And on one side, we have these grained pixels, which could resemble a small ice flows, and may confuse the model. So there's thankfully a partial solution to this, at least, or an alternative, using the NERSC noise correction. And this is this was the standard ESA one, and this is the NERSC one. And if we take a look again at these vertical lines, they are more or less gone. So we are looking at how is this affecting model performance. It's just a bit of data processing. We are reducing the SAR pixel spacing from 40 to 80 meters. And already we can see we start to see a bit more texture in the issues. And the second thing we do is increase the receptive field of the standard unit by adding additional layers and increasing how many pixels we can use to predict something. And using 5 levels instead of the standard 4 already increases the receptive field significantly, where we start seeing additional textures. And we can do it again. And now we see even more features. So here we compare models trained on the ESA noise correction and the NERSC noise correction, and we can see that just using the NERSC noise correction significantly improves even a smaller sized unit's performance. So this is only a 3-level unit, where we are this area is more or less correctly predicted. And if we then add additional layers, we can see we start to get increasingly homogeneous predictions. And that is a continuous trend throughout the levels here. So that goes from 3, 4, 5, and 6 levels unit. And here we can see that we have more or less, correctly classified this area.
1 minute.
And then we have done one with the 8 levels. And that looks like this. And there's a pretty strong resemblance between these two. There's still a couple of issues here, particularly the fjords, and then the intermediate sea ice concentrations in the middle. And this model is achieving a R2 score of 86% in comparison to what the tour presented. But remember, this is based on only one sensor. So this is the same scene as we saw before with the land-fast ice up here. And what we can see is that there's still some obstacles in this area, but we still get some part of it correctly predicted. So there's still some improvements to be made. All right. Thank you very much for the attention.
Excellent. Thank you. So there are questions in the chat. So would the presenters please have a look through the chat and try to answer ones that apply to them. We're going to move on to Torbjörn, who will talk about the Extreme Earth project results. We see your slides, we're not hearing you. You're showing as unmuted, so it may be a problem with your system. We're not hearing you. Do you want us to go on to the next speaker while you figure out your audio problems? Anton, are you ready to present? Okay, is that okay, Torbjörn? We'll go on to Anton and come back to you.
Can you hear me now?
Oh, yes.
Okay, then I'll just go back to my screen. Okay, so now you can see my screen? Okay.
Perfect.
Yes.
Thank you. Okay, so I will talk about some challenges in deep learning-based CS classification, lessons learned from the Extreme Earth project. Extreme Earth is a Horizon 2020 project that is focusing on deep learning techniques for computation of extreme analytics for Copernicus data. I would also add that we have another big project at the UIT called CIRFA, which is the Center for Research-Based Innovation, which is also focusing on CS classification from SAR. So when we talk about classification, it's about segmenting an image into various ice types. And here is an example of ice types. And what you see is that these ice surfaces are quite different. These are just a couple of examples. And it's the difference between these ice surfaces that we want the SAR to detect. However, as has been mentioned before, there are some challenges in SAR classification of sea ice. We have a dynamic surface. Its characteristics is depending on incidence angle. There is a noise problem. And when we look at deep learning techniques, they are usually needing a lot of training data in order to learn the weights of the system. When it comes to the incidence angle problem, it is a systematic power decay that you have over the image. As indicated here, you can see that on the left-hand side, the image is brighter than on the right-hand side. And this power decay is usually linear in the decibel domain. But the problem is that this slope of this decay is depending on the ice types. And there is a remarkable difference between the slope over water and over ice. So you could actually use the slope difference to classify between ice and water. The other problem is the noise that has been also mentioned before. It's related to how you create the white swath images, especially in the SAR, in the Sentinel-1 SAR, and where you have this noise pattern that is related to how you glue together the subswaths. And you see a profile there. There is some algorithms that is trying to remove this, but it doesn't always perform perfect. Then we have also dependencies of frequency and polarization, which sometimes could be, or which could have been exploited if we had some Thales observation. And this ROSE-L project that is run by ESA is addressing how we could could benefit from using observations in both C and L-band. And we have the seasonal variability. This is an image from the northeast coast of Greenland from April 17th, which is more or less winter conditions, and we can clearly see that there are differences between the different classes that we have in the images, where we have rough ice in the right-hand side and more smooth ice on the left-hand side. But if we go to the summer season, we see that the differences between the classes is kind of wiped out. So if you want to have an algorithm that perform automatic CS classification, we need to take this dependency of temperature into our algorithm. At UIT, we have developed a data set for exploiting deep learning algorithms, and this is based on 31 SAR scenes from Sentinel-1. And what we have done is combining information from optical images with SAR images and identified polygons, which we are quite sure of which type of ice that is in there. And then we have extracted patches of different sizes from these polygons. And the benefit of using optical and SAR is illustrated in this view graph, where we here see two examples of Sentinel-1 SAR images, where we have combined HH and HV in a pseudo color image, and we can see that there are clearly different segments in the image. We have a dark area where we think we see where we have leads, and down here we also have dark areas which probably are related to thin ice. And if you look at the optical images, we see how this can supplement our interpretation and help us in identifying which type of ice we are looking at. So we have made two data sets, one or three maybe we can say. One that is around the Svalbard area, which consists of these 31 scenes from Sentinel-1. And then we have some other data set that is from northeast coast of Greenland, where we have different images and over the season. And these images we are using for inference and validation. So in this presentation, I will only look into the ice versus water classification. And so we group together the water classes and the ice classes. And we have altogether around 20,000 in total for each class, and an approximately equal number of patches for the two classes that we are looking at. Then we are applying data augmentation, which is in this first test based on what they do in computer science. We know that there are some physical problems in applying these algorithms, but by using these, we are able to increase the number of patches by a factor of 10. And if you look at the we are testing out supervised classification using three different versions of networks. One that we call an ad hoc CNN, which is a fairly small network. Then we have applied this standard VGG16 network, which is quite deep. And then we have reduced the depth of the VGG using a modified version, which can take in smaller patches like 20 by 20. When we look at the learning curves, we see that if we do not add more data, the data set consisting of 20,000 patches will overfit, and that is also the case if we use transfer learning to learn the VGG16 network. Whereas if we apply this augmentation technique, we add more data set and more data to the training set, and we see that the learning is more should generalize better. So here are a couple of examples where we have used the data from Greenland to validate the performance of the algorithms. And we see that we have the problem with the noise, as we would expect. But in some cases, the networks perform really well. Of course, the noise issue will be a problem in further analysis. We also have looked into how we can get around the problem of scarce training data by using semi-supervised techniques. And here we have a model where we use two networks, a teacher and a student model, where we use the teacher model and train the teacher model in a first stage by using label data, and then use a technique where we take out the features that are detected in the first part of the network, and apply label propagation in the feature space using a graph technique. And then we, in this way, we apply pseudo labels to the student network, and then we do this in an iterative process and learn.
1 minute left.
Yeah, I'm almost done. So here are some examples of the results. So we get quite nice results, even with a very small number of label data. And in the inference, we used all the label data and added to random data that are unlabeled, and these are the results which looks quite promising. So the lessons that we can summarize here is that operational CIS charting would benefit from better understanding of SAR imaging of sea ice, improved understanding of SAR scattering from sea ice and polarimetry, improved methods for removal of the SAR system noise, multimodal data input, algorithms that are invariant or adaptive to changes in the properties. And our experience is that the deep learning models have excellent classification performance, but we need a lot of training data to achieve that. Deep learning methods also can remedy the scarce training data by data augmentation, but this should be done probably in a more physical aware way. We can use semi-supervised learning to extend our feature training data, and we can also use transfer learning, which is train the network by using data from another domain. And also deep learning offers methods for handling changes in data properties. I talked about then domain adaptation. So this is it. Thank you for your attention.
Great, thank you very much. I believe there's a question for you in the chat. Just a note to people asking questions, please put an indication of who you're asking the question to, because the chat's starting to get complicated. Excellent, so we're gonna move on to Anton. Yeah, great. Take it away, Anton.
Yes. Can you hear me?
We can.
Yeah, we can hear you.
And can you see my screen?
Yes.
These are two questions I usually start my presentation with the last 2 years. Today I will talk about not only classification of sea ice types, but also about assimilation of this information into a sea ice model. And I'm working at the Nansen Center in Bergen in the sea ice modeling group. And one of the tools that we are running at the Nansen Center and developing is NextSim. But unfortunately, I will not have a single second to talk in details about this wonderful model. I will just show the results because of the focus of this workshop. Next slide. I have already presented our algorithm in several fora. I will go very briefly over it. We also use Sentinel-1 SAR data on input from two bands, HH and HV. We don't do subsampling. We use it at native resolution of 40 meters in extra wide swath mode. And then for labels, we use ice charts from the National Ice Center. These are weekly ice charts. They contain information about both the ice concentration and stage of development. In some cases, form of ice, but not in the Fram Strait or where we have trained our model. And from these ice charts, we used sea ice type information. Unlike many algorithms presented, we don't use semantic segmentation. We rather follow approach, if I understood correctly, presented by Torbjörn. We split the image into small patches 50 by 50 and by 2 bands. And then we classify each patch into ice type using hot encoding. And we are trying to derive 4 cover types: open water, young ice, first year ice, and multi-year ice. And that's why our output vector has a length of 4. We also have been working on filtering the input data set so that we avoid the ambiguities of the ice charts, but I don't have time really to go into these details, maybe later. And then it's a simple convolutional neural network with a few convolutional max pooling layers and then a few dense layers in the end. And we used about 1 million labels for training and testing and validating the model. This is how our ice charts are looking compared to SAR mosaic and ice charts from NIC. So SAR mosaic on the left, our ice charts in the middle, and ice chart from NIC on the right. And it is one ice chart issued every week, and we can produce ice charts daily. So there are obviously some dissimilarities due to temporal evolution of sea ice, but generally the match with the ice chart is not too bad. Also, you can see the confusion matrix that for open water and for multi-year ice, the accuracy is the highest. But for intermediate classes like first year ice and young ice, the accuracy is a bit lower. Also due to uncertainties in the actual ice charts, not only due to errors in our algorithm. And for us, the main use of these ice charts is to improve predictions of sea ice and to provide a better forecast. So our next goal is to assimilate these ice charts into the model, into NextSim. And how do we do that? We observed that this ice type information that we derive from SAR is quite correlated with ice thickness that we can observe from CS2-SMOS. But of course, CS2-SMOS product is very smooth in both space and time. To obtain a map like that, there is an average of a week or even 2 weeks of data from altimeter and from passive microwave. So what we do is we take pixels according to our classification and average thickness over these pixels. And then we can build time series of thickness of each class as a function of time during the year. And we have training data not for the entire period, but only for some period, because in summer CS2-SMOS product is not available. But even during winter period, we can observe that the thickness of each individual type can be approximated by a sine line. And it is quite significantly varying for old ice, less varying for first-year ice, and is randomly varying for young ice category. Nevertheless, that is a good first-order approximation. So our assimilation scheme can be formalized as the following. First, we derive a stage of development using convolutional neural networks from SAR data. Then we compute A and B coefficients for each pixel as a function of stage of development. And then we use a simple sine formula, which depends on the date, and these A and B coefficients. So for each pixel and for each day in the year, we have a so-called observed CS thickness, which we efficiently compute from CS types. And then we do a simulation by a weighted average of the observed CS thickness and the simulated CS thickness. And weights are depending on the relationship between observed and model. So when observed ice thickness is higher, then we have a higher weight. And when it is lower, and then we trust the model more. So that we tend to overestimate the CS thickness a little bit. And then a few examples of validation. So here we have observations on the left and the simulation of CS concentration in the frame straight in the middle. And this is next output from the next C model and the difference between them on the right. And here no assimilation is performed and the differences are quite large. We obviously miss the ice edge. And when we do assimilation, right after we do assimilation, the fields are matching almost perfectly. Some differences are due to the weighted average and not just data insertion, but the ice edge is much better represented right after the assimilation. After 1 day, the differences are negligible, still negligible, and they are mostly in the ice pack due to the appearance of leads. And after 2 days, due to melting, we see a little bit of offset in the ice edge as well. So we can evaluate now. Yes? Sorry?
Just 1 minute left.
Yeah, so we can evaluate and say that after evaluation, the errors in CS concentration prediction are the lowest, shown by the orange line. The free run is the largest, shown by the blue line. And we see that we improve the skills of the model to predict CS concentration by simulation for at least 2 days. And here are just some animations that show CS concentration with everyday assimilation and you can see the updates, which are nicely visible. And you can see generation of leads by the next model. And also on the next slide is update of CI's thickness. You can clearly see the border where we perform a simulation. This is due to the limited area of CI's type product. And after some time, the difference between the ice thickness in the pack and where we simulate grows. But we are less concerned with it because our main goal is to improve representation of the ice edge, and assimilating this information helps a lot. I would like to stop here. Thank you for your attention.
Thank you very much, Anton. That was great. I would comment that there's lots of chat going on in the chat window, so please keep up with that. And we will move on to Julian. You ready?
Yes, I am. I guess as you can hear me because I'm in the same room as Anton.
Excellent.
And you see also my slides?
We can see your slides, yes,
Can
but
you see my
they're not in
slides?
center mode.
Just go to presentation mode.
Okay, great.
Sorry, switch your.
Oh,
we're
yeah,
seeing
okay.
Your view.
I never know how to do that. So, yeah. Yeah. Okay. Well, maybe stop sharing and share again. One, but I don't
No,
know how to do it. And start the presentation. I should start the presentation first, I guess. Yeah. Oh, yeah. Then I should share. I'm sorry about that. Okay.
okay, go to
Yeah,
presentation.
Okay, it should be okay now, right?
Not really. There, perfect.
No?
Perfect.
Yes, yes. Okay. Okay. So this is good. So thanks for having me to this very nice workshop. I will continue to speak about how we can combine model and data to improve CI's products. And I will talk especially on CI's thickness. So the challenge actually is the end challenge will be to represent accurately the CR interaction in polar region. And to do that, if you look at this animation from the next C model that Anton mentioned already, you see that the heat flux are very much drawn by large-scale atmospheric effect, but at the small scale, it's largely controlled by leads in the ice. So all those small leads are very visible on the animation. So yeah, there is a strong influence of small-scale features of sea ice to the heat flux representation. And if we want to represent well this influence, so we can rely on either models or observation. If you look at the representation of the scale in the observation in the model, on the left side you have the next simulated output of CI thickness, where you see that the cracks are very well resolved, but of course they are not observations, so they cannot be located exactly at the right place. On the right, you have observations that represent exactly what we can see, but you see that observations, so here this is CI2 product, are at much coarser resolution. So if the question is to resolve the cracks resolution, we see that we can do it with the model, and the observations are still too low resolution to represent well those cracks. So the idea of this work, the general idea, is to train an AI algorithm. So here it's a CNN combined with ResNet. I won't go too much into detail in the architecture, but you train the idea is to train the algorithm on model outputs, and to apply, so on the top, and then to apply the AI model, so the machine learning model, to observed CIS products, such as CIS2 for example, to obtain new CIS projects, such as high-resolution CIS thickness. So this is what we do here. So we have 4 inputs, so deformation of CIs, concentration, and CI thickness at a medium resolution to mimic the actual resolution of the satellite. So all these images, all those fields have been obtained from the model, but with a by smoothing the model output to represent the satellite actual resolution. And then we have also from the model the high resolution CI thickness. So we learn, we train the neural networks to predict the high resolution CI thickness from low to medium resolution source. So here is the first result we have obtained here, still on the model data. So you have on the left side a very simple baseline, which is a product of CIS concentration with the medium resolution with the low resolution CIS thickness. Here you have the truth on the middle panel, the truth. So what we aim at, getting, and on the right side you have the output of the neural net. So you see already that neural net is able to represent some small scale, maybe not as much small scale as the truth, but still much more than the baseline, and much more than that we have in the input field. So here, to be a bit convinced of the reliability of the method, you have the evolution of this product still on the model data as a function of the time. So you see the evolution that are quite representative of the cracks. So we can represent quite much better the cracks and also the ridges in the CIS. Also, one thing to mention is even if we represent well some small-scale features, the idea is more to represent the distribution of CI thickness within the size of a low-resolution pixel, so within the size of a pixel given by the model, for example, because this is what will have an impact on the heat flux, for example. So here you see that at the size of what we call super pixel, so the resolution of the satellite product, you see the difference between the baseline, which is basically the low resolution product, the truth CI thickness, and the neural net output. And if you look at the distribution of CI thickness, and in particular the distribution of thin ice, you see that the output of the neural net within this super pixel are more able to represent the distribution of the CI thickness. So this is what you obtain in a model world. So now the second step is to apply this algorithm and this model to actual satellite data. And this is the next slide. So here we show you for January 2021. So here is on the left is input, one of the input of the neural net model. So the CIS2 product of CI thickness with small, only large scales or medium resolution. Here we have two versions of the neural network model. One takes as an input ice drift derived from passive microwave, so deformation derived from ice drift from passive microwave. So on the middle, so you have a larger coverage but a smaller resolution. Here on the right side, you have another neural network that also have been trained from model simulation, but they take into input ice drift derived from SAR data. So as a much higher resolution, and you can see that even though the coverage is not as good as for passive microwave, we have a much better resolution that are represented in the SAR version of the CNN. So yeah, so this is basically what we have done. So we have trained a neural network approach on model data. So the neural is only trained on model data and apply it to satellite data to enhance the resolution of satellite products and to better represent the CIS thickness distribution in one grid cell. We at the moment we are validating this result, and it's quite promising using Cryosat-2 data. And of course, there are many applications of this result. So, as Anton showed previously, this product can be assimilated within the CI thickness. The CI thickness distribution can be assimilated within a model to better represent the CI thickness and the heat flux in the model forecast. Of course, it will improve the localization of cracks and leads in a numerical model, and also hopefully improve also the estimation of heat flux. And it can be done also only from the satellite data. So from satellite data, we can have an improved product for heat flux. So this is what I have. This is my email. I've left my email, so you can contact me for any question regarding this work. Thanks.
Excellent. Thank you very much. So, Alyssa, I believe you've now joined us. Excellent. Are you
Yes.
ready?
Hi. Can everybody hear me? Yeah.
Yes.
Yes. So thank you for having me. So I'm going to share my screen, and can you tell me if you see it? Well, yes. Is everything?
We see it. Perfect.
Yeah, great. Can you hear me well, or do I need to up the volume or something?
We can hear you.
Okay, great. So, good afternoon, everybody. So my name is Elisa. I'm a master's student at the National School of Geographical Sciences in Paris. And so I'm going to present my work I did during my summer internship with Anton at the Nansen Center. So I did some work on and I will show the improvements and uncertainty in convolutional neural networks CI step classification. So what I did, and I also got some help from Julien during this internship. So just briefly, the summary of the short presentation. So the context and state of the art, then the methodology I applied and the results, and then some quick conclusion. So we worked with data from the eastern coast of Greenland, which is surrounded by floating ice, which represents danger for navigation and also for local people who want to navigate here and move. And so we used different types of data. So SAR images for the eastern coast of Greenland, then brightness, temperature, passive microwave data from AMSR2. And then our target data were ice charts. So here you can see an example of ice chart for the region with the different partial concentrations, ice types, etc. And so we used the SIP version 2 data set, and then we moved on to the version to the third version. So we based the work on different other papers. So the first one was the sea ice and water classification using CNN that was done by someone from my school previously. And then we also based on work on the combination of AMSR2 data to sea ice and water classification. So here you can see an example with the result of the inference for water above, then in the middle for ice, and then the ground truth below. And so we also used one-hot encoding from a paper that is to be published this year. I don't know if it was published yet. So we wanted to automate ice chart production and classify sea ice types, and also combine SAR and AMSR2 data. And one of the goals was also to test different configurations of CNN to see which were the best ones and for different seasons. And so we also wanted then to apply the chosen configurations on some scenes that we had. So for the SIP version 2 dataset, we worked with this kind of, so with these types of data. So obviously SAR, passive microwave, here you have an example. So we used all frequencies in both polarizations. And then here you have the an example for the one-hot encoded, data. So for the ice charts, so you have water, first-year ice, and multi-year ice. So we used only those three classes. And here on the pictures, you can see the partial concentrations. So it is one of the one-hot encoding methods that we used. So about one-hot encoding, we used on ice charts, we consider that is a collection of pixels. So you have the same partial concentration and same combination of ICEPs for each pixel. So we had a problem with water pixel misrepresentation, but I'm going to talk about it a bit later. So we use the binary one-hot encoding, so that it is the traditional way with assigning 1 to the maximal partial concentration and 0 to the others. And so we also used the continuous method that was described by Tamber et al. So we used partial concentrations as soft probabilities and assigned it to all elements of the output matrix. So here you can see an example of the possible combinations that we did just below here in the table. So then we tested the different configurations of CNN. So we used the basic structure that was provided by Julien Brajat that worked on chorus segmentation. So it worked well. And then we tried to test a hyperparameter. So we did a heuristic manual approach based on loss functions. So different loss functions described here. And on the upper right part of the slide, you can see the hyperparameters we tested. So the number of convolutional field layers, the depth of the unit, the batch sizes, and also the methods of encoding, which were very important for us. And then we did some visualization on some selected patches, so smaller images from the inference data set. So here, just for an example, one of the selected final configurations of a CNN that we used. So then we did an inference on 2 scenes. So we did our training on 5 different scenes, the validation on 2 different scenes, and then the inference on 2 separate scenes that were not in the validation nor in the training to avoid contamination. So here are just some examples of the inference. So we used a summer scene and a winter scene. You have the SAR images on the upper part, then the ice charts as described before, and then you have the inferences. So here, for summer, you can see a good classification visually for water, somewhat good for multi-year ice. With first-year ice, it's still a bit lacking. So it was one of so it was the configuration that we chose for summer, and for the winter, the same configuration gives us worse results. So somewhat good for water, first-year ice and multi-year ice are completely mismatched. So we selected another configuration that is showed in the technical report. And so just visually, we could not just conclude. We did confusion matrices. So as I said before, visually, we have a good classification for water, a good classification for multi-year ice, but here you can see for first-year ice, it is completely it's very bad, actually. So, and for winter, the other selected configuration, again, good for water, a bit worse for multi-year ice, and then first-year ice, you see it's completely mismatched here. So as a conclusion, we tested different configurations of CNN, so 5 configurations in total. So we tested them automatically and heuristically manually. Then we selected 2 configurations as best one and applied to different scenes. So 1 configuration for summer, 1 configuration for winter. And so for the first time, we did semantic segmentation to both SAR and answer2 data for CICEP classification. So it is a good classification, but still with some errors. So between first-year ice and multi-year ice. And so the main sources of errors are the similar backscatter and also ice chart errors. So the ice chart are done every day. So that means by experts. So that means there are some potential mistakes and errors in the ice charts. And also the misrepresentation of water. So that we also have errors related to that. And so there was a bit of a problem because we worked with a limited data set. So as I said, 5 scenes for training, that's a short amount of scenes and also in a short time period. So we worked with data from 2018 and 2019. And so it would be better to work in the future with a different data set, with a larger data set, and over more recent years or even previous years. So if you're interested, the codes and the notebooks with the visualization are available on the NERSC GitHub, and the technical report was given to Nansen Center. So and it is to be published. And so one of the other solutions to improve the work we did during this internship would be to test the methods of improving ground truth. So there are two methods that were proposed by Temper et al. So the first is augmentation with SAR data, so combining SAR data and ice charts. So that would reduce the errors linked to water pixel misrepresentation. And also the random methods to modify the ground truth showed some good results. So thank you for your attention, and thank you for having
me. Thank you very much. And unbelievably, we're actually ahead of time. So we can go, Lisa, there's a question here, which maybe you could answer. Can you read it, or do you want me to read it to you?
So about the partial concentration?
Yes.
So we used a partial concentration for the continuous one-hot decoding method, so as soft probability. So I can probably show you again the table we used. Just a second. Yeah, so Anton actually answered a bit to this question. So yes, we use the partial concentration to every, so to yeah, sorry. Okay, I understand the question. Yeah, so if you are interested, yeah, probably the ice chart quality. So if you want to discuss it, I think I have my email somewhere, or you can discuss it with Anton. He's my supervisor. So
excellent.
Yeah, thank you very much for having me.
Okay, thank you. We'll now move on to Dimitri. Are you there?
Yes, I'm here.
Excellent.
And I hope you are seeing the screen now.
We are. If you could just go into presentation mode.
Yes, sure. Okay, so I'd like to share our work at DLR, at German Aerospace Center, about ice mapping. And actually, a part of many others, our motivation is a bit different. So I will focus a bit more on that, because here at the Maritime and Safety and Security Lab, we don't have models, we don't run models, but we are interested in well, safety, including safety of operations in the Arctic. So we are looking for in providing some aid for better navigation in the Arctic areas, and of course for that we would need the ice maps. So on top you can see a large scale map of ice concentration from AMSA 2, and though this is the kind of the data that is currently used for route planning on, so to say, long term. That is, together with forecast, one can plan for the several days where to go, how to go, and where not to go. The question is what happens when we are already in the ice, and what's the best route through the ice pack? So that's, so to say, tactic planning. So currently the ice radars installed on board are used. In some cases, helicopter flight can be used, but that's pretty rare. And of course, satellite images. One of the issues, the internet connection in the Arctic is far from being perfect, but also not all icebreaker crews use SAR just because they don't have enough expertise to derive some information from those. So we are looking for providing this information in an easy and compact way. And because we are looking into really fine resolution classification, we are not using ice charts that are coarse, and that of course includes some errors, but we are labeling data by ourselves. So here you can see comparison of Sentinel-1 and Sentinel-2 optical data. And basically by comparing these images, whenever we have overlap in area and time, we can actually see many various ice types. So with the help of optical data, we can confirm that, okay, this is indeed a gray ice forming or new ice forming. Instead of doing box labeling, like it was mentioned by Torbjörn, we are doing well, this is basically pixel-wise labeling. Of course, we are not choosing every pixel, but we use GIMP software and the tools that smart selection tools that they provide. And this way we can really select areas or regions of an arbitrary shape. And of course, because of the noise throughout the images, we can adjust the thresholds so that our selection is consistent both in the first and the fifth swath, for example. Yeah, so we recognize 6 surface types currently, and actually we see potential for more. Yeah, you can see those. So multi-years, first-year ice, new ice. We have 2 types of open water and very thin ice, and also rough ice, which might include some frost flowers or yeah, reached areas. For the classification, we use UNet++ network, that is updated UNet network, which so advantage is that it combines features of different scales on every level of the model, which leads to a better performance. We increase depth of the left part of the scheme, so we have larger area that is analyzed, but the right hand, the part on the right hand has not been increased, which means that the result of our classification is 4 times lower, which from one hand saves us time in those investigations, but also we consider that features that are smaller than 160 meters meters in size, they are too small to be used for reliably for navigation, or that can be suggested for navigation purposes. And here you can see on the right the result of, okay, sorry, I think I go one slide back again. So on the bottom right, you can see the labels that we do, and the blue is the unlabeled area. So we do not label the entire image, but just some areas where we are sure. And here this is the result for the same image, but yeah. So this is basically the data that was, it partly contains the data that was used for training. So this is also called semi-supervised learning, and then we apply this for unknown data. One of the issues we had with this fine scale thing is that you can see on the left side we have effects from the tiling. So when we cut our image into tiles, classify them and join them together, we have clear an effect of that, which we reuse by doing the classification 4 times, and every time we cut our image into labels with an offset. So this smoothen the result. And as a result, we are getting those maps on the right side, that's next to Greenland. And what's next? Once you have this map, we could provide it for the ship, but we don't know how ice conditions will change with time. And for that, our colleagues from Drift and Noise apply a ice prediction model that predicts how the ice field will look in the next hours. So basically on an hourly basis. So we had a project for that. And then those, a sequence of these maps, of the forecasted maps, are fed into optimal route estimation algorithm that is run at the University of Bremen, which then predicts the best route through the ice from as we can suggest. And as an example, I have a animation here. I hope it will work. So imagine that we are over here. I hope you see my mouse. Okay, in the lower left corner, and we want to go to the red dot in the upper right corner. And then the algorithm predicts how we should go the best. Yeah, so this is still to be tested, and during Corona, of course, validation of those was very, very limited. But yeah, thank you for your attention, and I'm happy to answer questions if you have any.
Great, thank you. We are now ready to head into the break, and we are about 15 minutes early. Embarrassing situation to be in. Before we move into the break, I'll just open it up to questions, either to Dimitri or any of the previous speakers. There's been good chat in the chat box. Is there anything somebody would like to? In fact, Andreas, I'm not sure, do we have the capability to unmute attendees?
I don't know. I can try.
I think we can.
Yeah,
So if you would
normally,
like to
yes.
say some,
Mm-hmm.
if you'd like to say something, Melanie, can we unmute everybody?
Yeah, actually, I have several questions in the chat, so I could comment on those if that's fine. So I
Please
think
go
I will.
ahead, and but it would be good if we could maybe just open it up to a discussion session if we can unmute everybody. But go ahead and answer those questions.
I will start with the last one. The number of training samples is quite limited. I think it's a bit more than 10. So we were just testing how that works. Of course, this is nothing comparable with ice charts or with what was presented before. But we have, on the other hand, a smaller but a fine scale labels. As for converging and diverging, I'm not 100% sure because this is more depends on the model that is used, and I'm not aware of the details. I think it should work. So it is not just shifting everything, with the wind and currents. So it should treat different features separately, but I'm not 100% sure.
Do we have the capability to take audio questions from the attendees? Melanie?
We can unmute people. We can request people to unmute.
Yeah, actually, we can have questions on chat.
Okay, but we can't get everybody involved.
The only button I can see is called mute all, which is the opposite.
Okay. We've got one more question there. I believe it's directed at Dimitri. Do you see it there, Dimitri?
Yes, right. So we found that the performance of UNet++ is higher than for UNet, but I can't provide any like number that this is this higher. And this comes just from the fact that it takes the features from every layer, basically every layer, and for the upper layer, so to say, it upscales them and use them all together. Though you shouldn't expect that it's drastically better. I think better you just test it.
Okay. Good. Well, what I would suggest is we come back at 10 minutes to the hour. If there are no other questions, is that good for you, Andreas? Okay. And we'll start off with the next speaker. So we'll see you all then. Can you start?
Should I start now?
Yes, please.
Oh, no, I was waiting still a few minutes. Okay. Okay, so presentation on understanding changes in polar areas using satellite image time series of Sentinel-1. So the objectives are to create a benchmark data set by extracting knowledge from the user to understand the temporal evolution of the surface of sea ice for a period of two years, and we are working to extend it, and to prototype explainable artificial intelligence methods to achieve these targets. So I would like to position our work. So we cover the field of Earth observation, mainly synthetic aperture radar observation, at intersection with explainable artificial intelligence, and particularly on machine learning, explainable machine learning. The goal is mainly to provide trustworthy methods for analyzing big data of high complexity. A short reminder of our methodology. So actually we established an explainable paradigm for Earth observation. We apply it to synthetic aperture radar, but it's not limited to synthetic aperture radar. So we have a processing chain with two branches. One which is supervised based on active learning, and one which is unsupervised based on a Bayesian generative model, latent direct allocation. The active learning, actually, it's interrogating an expert. The expert is choosing the training samples, positive and negative, and generate semantic classes. The semantic classes are actually gathering the knowledge of the expert. So the expert is injecting his knowledge in the data set which was generated by active learning. Latent direct allocation is an unsupervised method initially used for text analysis, in which we extract seamless words from the Sentinel data. So we are not using any feature, we are using directly the samples of the Sentinel data from the dual pol in such a way to be unbiased in the generation of the topics. And latent direct allocation, it's indicating which are the topics and their probabilities. This means we have a model of the data itself, the innate model of the data. These two are analyzed by statistical methods, computing correlation, concurrences in between various classes, or implementing classification like dyadical or tree classification. What we obtain explanation of the sea ice cover, like floating ice or iceberg classes, for examples, in terms of the contribution of the topics. The topics are used as an intermediate level, which allows to explain, analyzing this consistency of the composition of semantic classes by the topic. It is a way to analyze, and from this we extract classification, which actually explains the nature. So here we have dyadic classification, which is grouping one cluster, like floating ice, water body, melted snow, as a second cluster, glacier, young ice, iceberg. So second one, it's relating to solid ice. The second, it's related to melted ice and water. So this is a way how the data was explained in an automatic way. We continue to develop these tools with specificity for satellite image time series. So satellite image time series are data cubes, which in addition to the complexity of the SAR image, SAR records, they have the complexity of long-term observation. And these tools allow us to manipulate a data cube. In our case, a data cube of 24 observation covering 2 years. The graphical interface is linked to a database, and the user can perform one of the simplest operation queries in such a way that can evaluate the evolution of classes. In here we have using the classes defined by our colleagues in Tromsø, by Nick, black border, floating ice, glacier, iceberg, melted mountains, old ice, first year young ice, water current and water bodies. And we group together the classes marked in red, which have been indicated by our explainability paradigm. We group them in a separate class. The query is done in an interactive way, so the user can click on one of the images of time series, and the tool is retrieving all the images in the time series. It's another example of querying. So here one could observe already variation over the season. Another example was that are other discontinuities in the time series in the sea ice cover. However, this analysis, this visual analysis, it's quite involving. It's a difficult task for visual analysis. It's not easy to understand the data. And here we developed a tool, a specialized tool for visualization of time series. So we start with a change map from our time series. This time series is analyzed using latent directly allocation, extracting the topics. And the time series of topics, it is analyzed to obtain a classification of change maps. So each class actually represents not a sea ice cover at a certain time class, but it's a class of evolution. So one color means all the patches under this class, they have a similar evolution. These classes of evolution, they are ruled by the dyadic classification in the category of sea ice covered to related to water, like melted ice and similar classes, and solid classes. So this is a map of classification, and each of these streams represents visualization of the classes over the time. So we, instead of visualizing time series and classes, individual classes, which is almost impossible for given the high data volume, we extract evolution of classes and to represent like code. So this color code, it's a visualization which allows to understand the evolution, having, of course, the legend of a classification provided by the SVM, the active learning, and the latent decay allocation, the explainability. So with this tool, we enable now users to evaluate large volumes of data for CIs. And this is a tool we are using now in externals to better understand long time series. We are working now to extend the time series for another period of time. So I thank you, and if there are questions.
Thank you very much for your overview on your explainable AI. I don't see any questions in the chat, but maybe could you elaborate a bit on your I saw in your slide that you were using a Bayesian generative model. Is that your hierarchical cluster?
Yes, so actually not, I don't have too much in these slides about the theoretical aspects. So in here, this is a slide you indicated, yes?
No, it's a bit later.
This one? You stopped me when...
This one. No, yeah, the one before. Previous one, this one.
Okay, so in here, we have a labeling which is effectuated for all the time series. The labeling is done without the time information. So we label all the data tube with the classes which are marked on this legend. So that is done using the active learning, and that is based on the previous analysis of the topics which have been extracted from the data. So we are using an unsupervised, completely unsupervised method, the latent decay, which indicates actually the composition. So which are the components of semantic classes. And based on this, we are labeling the entire database. The database in this moment can be classified in classes of evolution as the classes which are here. However, these classes of evolution, they are not really revealing the dynamic of the CIS cover. And to have the dynamic of CIS cover, we generate this visual code. So the visual code shows, I go to this, shows in the evolution over the 2 years, the sequence of semantic classes. So in here we have an evolution from old eyes, so magenta, to first year eyes, which later goes to young eyes, is changing on a mountain. That is an artifact in the data, in the classification. And later we continue with old eyes. One of the classes is a water group. So melted eyes, we have been grouping all of this, and we continue to analyze it in this way.
Okay, thank you. Then I think it's time that we continue to our next speaker, Nabil. Are you able to share your screen? Great.
Am I audible? Can you confirm, please?
Yes, we can hear you and we can see the screen. You can start from there, please.
So I'll start. Hi, I'm Nabil Panchi, and I'm a PhD candidate at the Department of Marine Technology at NTNU in Sondheim. And along with my supervisor, Professor Ekaterina Hakim, I've been working on challenges of deep learning in context of its application to the Arctic. But we are looking at things from the ground level. We don't work with satellite data. We work with optical images that are taken from ships and ground stations. So today we will be looking at the application of how can we use optical images from ships in order to generate some validation data for satellite-based products. So what we see is that we all know that sea ice extent has been reducing, and there's been an increase of about 5% in the number of ships entering the Arctic, and this data is from Arctic Council. With more ships operating there, we are collecting more data, more optical images as well as video feed from the. So more data means it should be really good for us, right? However, it's not that simple. All this data needs to be processed by ice experts, which are data and convert this into useful information. But why is that important? So we have been talking about the quality of ice charts and using ice to use or not use ice charts as validation for machine learning models. So this is an alternative to ice charts, or at least this won't replace ice charts as such, but it can be used in conjunction with ice charts because this is ground level data. So it has a very high resolution, but the spatial resolution is not that high. Now these basically are georeferenced images from ships, and then we can compare those georeferenced images with the satellite product. And the most important part here is that it is very scalable, because since we are using deep learning, we could just thousands of images if you like. So we don't we need limited input from ice experts. Okay, so this is what our deep learning pipeline looks like. We have a set of neural networks, to be precise, which take an image, 512 by 512 image as the input, and then they produce then we have an ensemble module that will take the outputs from the neural networks, and finally we have a post-processing module which will remove any unwanted noise, right? So okay, so since we are working with supervised learning, we need some data set to train our models. Since there is absolutely no segmentation data set, especially ice segmentation, right? We had to create our own. We collected lots of images or whatever we could find on the web, and then we generated labels like these by we manually labeled these, and then we then pre-processed our data set because we saw that the data set was very imbalanced. That is one class, that is sky and open water. There were like 300 images that contained open water, but only 30 that contained surf flow bits. So we used a sliding window based pre-processing technique to oversample from the images that we already have. And we are looking at 14 different classes. Out of those 14 classes, 10 of them are ice objects and 4 of them are non-ice objects. Non-ice objects as in sky, open water, and melt ponds, and shore also. Okay, so now let's look at some results from the segmentation. The mechanism or the pipeline that I showed you works reasonably well. I mean, as well as on any other state-of-the-art method on other segmentation data sets, such as so this is it works with the mean IOU of 0.79, and we found that there are some easy classes to predict, and then there are some difficult classes. Easy classes would be sky, ice flow. These are some qualitative predictions, qualitative results from on the left is the one predicted, and on the right is the true. So for the first image, we see that the model predicts level ice very well, as well as deformed ice. But at the back, there is some shore visible in the true label, but the model doesn't capture that. It thinks that all of it is deformed ice. Second one is done very well by the model. In the third one, we again see some with the boundary of the ice flow, and we also see some noise, even though we have tried to remove all the noise that we can. Okay, now, as I told you, we have two categories, major categories of ice objects, major categories of classes. First one is ice objects that are basically pieces of different types and different. Then we have some non-ice. We wanted to understand if the model performs equally well on both of them or differently. So we plotted this graph presents the mean intersection over the mean score for ice objects, the purple bars and the green bars for non-ice objects. And we have three types of test sets. The first one is clear test set without any distortions in the image, and then we have a grayscale test set without any color, so normal test set but without any color. And then we have a test set in which we have applied a vignetting. So this is to simulate artificially. We see that the grayscale test set, right? In the grayscale test set, there is a loss in performance in the ice objects. So basically, color is important if you want to tell between them. See that when visibility is reduced, there is a huge loss in performance. Finally, if you really want to differentiate between ice versus no ice, we realize that our model works way too well for that, almost with more than 95% mean IIU, right? And even here, we see that if we reduce the visibility artificially, we see a drop in performance. So is it all perfect? Well, we see some challenges. First of them is limited training images. You don't generally find open access ice images online. And there are some images in the data set such as ImageNet, but to begin with, it's not for segmentation. And secondly, the labels that they provide are mostly not accurate. And there's only one ice object in the entire image, which is not the case in the wild, so to say. And things that obscure visibility in any way, that is fog and darkness, can be a real challenge for deep learning models. Then we find that there are two types of classes that were really difficult. One of them is Floberg and melt ponds. We tried to understand why melt ponds were difficult to predict. We thought that maybe these melt ponds are really small, and that's. However, it turns out that there are other classes which are also small as a fraction of the image, but the model was able to predict them well. In the end, we realized that since melt ponds, there was not enough data on melt ponds and Floberg. So maybe that is why the model doesn't really learn them very well. Okay. Now this is one of, let's look at some first prediction, I guess. So the first one is the best prediction. We see that images that have classes such as deformed ice, sky, and level ice, or a combination of them, the model tends to work really well with those images. While we see that images that contain melt ponds or Flobergs, the model doesn't do so well with those. So where we see the application of this, we see the application. We can use our model to supplement the ice experts, and we can provide a high temporal resolution because we can put this model on top of a vessel which is operating in the Arctic, and it will give you real time. Finally, we can calculate some ice concentration by using a pre-calibrated mesh. We can also extend our model easily for it to be able to tell us the ice age as well as the thickness. And then, yeah, this is just a demo of Yeah, thank you. If you have any questions, I will be very happy to answer.
Thank you very much, Nabil, for presenting your work on this alternative form of CIS validation. I do not see any questions in media chat, but I came to think about what type of ships will be able to give you this type of information.
So there are some.
Your audio disappeared. Can you try to repeat?
There are some icebreakers operating in the Arctic, which right now are collecting data, basically a video feed from cameras on board. And those data are, mind you, that they are not openly available, but if we partner up with some icebreaker or some commercial ships operating in the world, we can get a video feed in real time.
Okay. So you have to build a big network of commercial shipping vessels, I guess.
Yeah, that's the plan eventually.
Also, I see you have a question in the chat.
Yeah. How do you deal with different lighting and lighting as a significant? Yes. So firstly, we think that lighting, in the sense that if the light goes down, if the visibility is low, but things are visible, but the brightness is low, it doesn't really matter, because we always normalize the images before passing it to the neural network, so it doesn't really matter. But if things are obscured, if there is pitch black, then it becomes really difficult for us, for the model, and significant influence on the color, and that is why we tried with the grayscale images. Turns out that the model, if you want to tell between ice and non-ice objects, then it's easy to do it without color. But if you want to be able to tell between ice types, then there is some increased confusion between, let's say, level ice and some other types of ice, if there is no color.
Yeah, sorry, I was not meaning that something is not visible, but as sun goes on the sky, the lighting conditions change. And depending on the sun elevation angle, the colors can also change. Was that taken into account? Because for satellites, normally you have a fixed time when the satellite overpasses. But pictures from ship, you don't have this data.
Oh, so in that, the data set that we have collected, it has almost all types. We have sun on the horizon as well. We have sun up. So we found that the model generalizes very well across those types of images. But then after the sun goes down, then it becomes a problem.
Thank you.
All right, thank you, Nabil. I'd like to invite our next speaker, Jessica Cartwright from Spire. We cannot hear you, Jessica.
Right.
Yeah, that's better. We can see your screen.
Good, wonderful. Here I go then. Hi there, I'm from Spire Global, and I'll be sharing some new ice measurements and products that we have from our nano satellite constellation, and how we've been applying decision tree supervised learning methods using XGBoost to classify ice types, with the hope that they might be able to aid ice mapping and charting in the future. First, I'll introduce our constellation and then talk a bit about the measurements themselves. These measurements are currently sea ice detection and classification, as well as sea ice altimetry. A bit about Spire. So we aim to provide long-term sustainable monitoring through these techniques, and are known for doing things quite rapidly. So from the design of the satellite to launching an operational collection of measurements, this allows fast iteration on techniques and real-time improvements. And all of this is facilitated by performing as many of these as possible in-house. So an example of this versatility is our radio occultation satellites that we have in orbit. These are relied upon to provide critical data for numerical weather prediction worldwide. but we observed that they could also be used as sea ice sensors, so they're doing that now too. We've launched over 100 nanosatellites to observe the Earth for the purposes of atmospheric and ionospheric sounding through our radio occultation measurements. These can be seen as the red dotted lines on the picture here, and they represent the direct signal received by our satellites from the Global Navigation Satellite System transmitters. So, for example, GPS or Galileo, after being altered by the atmosphere. In order to measure the surface, we've reprogrammed these satellites to track the reflected component of the signal. So here this is seen as the green solid path. And this allows us to compare the direct and reflected parts of the signal to understand the surface characteristics. For example, soil moisture, ocean winds, and in this case, sea ice through GNSSR. So that's Global Navigation Satellite Systems Reflectometry. GNSSR can be considered a form of bistatic radar. So it uses the GNSS satellites as L-band signal transmitters. And at this frequency, we can penetrate clouds, and the scattering regime at the surface can inform on the surface classification through roughness estimation and reflectivity. Primarily, the advantages of GNSSR are that it only needs a receiver in orbit, as it's very low mass and low power. Another advantage is that over coherent surfaces such as sea ice, we expect the footprint of each measurement to be relatively small for a passive technique, about 0.5 kilometer across track and 1 to 6 kilometers along track, depending on the averaging performed through the processing. This combination of good value for money and small footprints means that it lends itself to a constellation mission, allowing the resolution in both time and space to be improved through the introduction of more platforms. Here are two of our types of satellites. So on the top are the data we're showing, are the ones that we're showing the data from today, and on the bottom are our purpose-built GNSSR satellites. So the grazing angle data comes as amplitude and phase information, which we use to calculate the coherence of the signal through the variation of the phase. More coherent or smoother surfaces are expected to exhibit a steady change in phase, and rougher ones are more noisy one. The use of this phase data means we don't need to be concerned with calibration. Example maps can be seen here, and the ice edge and ice types in the Arctic are clearly visible. Here's another variable that we're calling excess phase noise. This can be thought of as the phase noise metric, with the component depending on the amplitude removed. In these videos, you can see their sensitivity in particular to the Antarctic marginal ice zone and ice type distributions. So the first step in the ice classification was to separate the ice from the water. And here you can see our really simple algorithm trained with 1 week of data from March 2020 as a function of the elevation angle of the observation seen on the left. The histograms are divided into sea ice and water on the top, and first-year ice and multi-year ice on the bottom row. I won't go into too much detail about this, but we trained on 1 week of data in March 2020 to create the thresholds and have applied them across the data ever since. This is performed first for ice detection and then for binary ice types, so first year versus multi-year on the ice points. On the right, we can see the product itself and the rate of agreement against passive, active, and operational data products. And here's a quick illustration of the simple thresholding algorithm on the left and the binary product itself on the right. These data are being operationally produced in our processing system with data back to February 2020. So on application of machine learning to this problem using XGBoost, we compared not only with the OSISAF product we showed in the last slides, but also with ice charts from ARI and the National Ice Centre, here dividing first year ice and multi-year ice at code 95. So that is between first year ice and old ice. In order to account for the inclusion of many different classes in these two new classes, a spatial buffer was applied to the edge of each class polygon. This removes the data in the boundary region to ensure that the data from the marginal cases and mixed class types do not affect the training of the model. We found our best results came from training on all 3 comparison data sets at once, with the reflectivity, phase noise, and excess phase noise derived variables, in addition to the elevation angle of the observation, using training data from 2020 and testing across all the data from 2021. We've optimized the hyperparameters of the model for the best output. The ROC curves on the right show a large improvement of the XGBoost model. So that's in the solid yellow, the curve, over the simple thresholding algorithm, which is in the blue, this one here. when comparing our classifications to the ARRI ice chart classifications for the same location and time. These show improvements in all skill scores with higher Matthews correlation coefficients, area under the curve, and simple accuracy. The performance can be compared to the agreement with the National Ice Centre ice chart and the OSCSAT ice product. That's the other two lines here, which can be considered the upper limit of the potential performance using this technique. The calibration curve at the bottom displays the good calibration of the model. So that's the solid yellow line again, not straying too far from the one-to-one line, which is the dashed black line, indicating that we can rely on the output of the model to accurately self-report the probabilities. We found the calibration was slightly poorer when using the US National Ice Centre ice charts or the OSCSAT datasets as targets, and we think this is probably primarily due to the underlying differences between the datasets, as well as the location and class imbalances within each dataset individually. So smaller scale studies of the phase noise data have yielded matches between the GNSSR variables and the multi-class classification seen on the ice charts. So for example, the Sentinel-1 image on the right shows a diverse ice field with different ice types from the ice charts shown in the image to the left. Overlaying the GNSSR data on these images shows them to co-vary over different ice types, with new ice more coherent than older first-year ice. As such, we can go further with our surface delineation, attempting a multi-class classification. In order to account for the significant imbalance of the class sizes in the ice charts, as well as the overlapping class types, for example, first-year ice, thin first-year ice, medium first-year ice, and misalignments between the different ice chart providers, we have trained on the collations of the stage of development codes and termed these as young ice, first-year ice, and old ice. We can see from the ROC curves on the right and their associated skill scores that we're able to achieve a large increase in Matthews correlation coefficient against the binary classification in the young ice especially. So that's increased from 0.402 for the first year ice in the last slides to 0.514 for the young ice here. This, along with the decrease in skill score for the first year ice class, here shows that the GNSSR data is likely most sensitive to the youngest stages of development of sea ice. It must be noted that unlike the binary classification, no boundary edge buffer was applied to these data due to the smaller, more pocket-like nature of the younger ice types. This will lead to more ambiguous samples in the training and testing datasets, impacting the attainable model performance. And this shows up as a significant reduction in the agreement between the two different ice chart datasets from the National Ice Centre and the Russian ones. In this context, the significant improvement in the model performance for young ice is particularly remarkable, and the agreement between the SPIRE measurements and the ARRI classifications is competitive with the agreement between the ARRI and NIC classifications. This high sensitivity to the youngest stages of ice might be linked to the higher proportion of younger ice types seen in the marginal ice zone, and how clearly this shows up in the excess phase noise variable we showed earlier. This is in agreement with L-band studies, such as from SMOS, where L-band is most sensitive to the changes in thinner ice types. Studies into the dependence of the model output on the variables themselves have yielded insights that the youngest ice type is associated with the lowest coherent reflections, first year ice highest coherent reflections, and old ice medium values of coherence in the reflections. So we've shown some results over the polar zone using SPIRE's nanosatellite constellation to show that these measurements largely agree with external sources with potential to deliver high spatial resolution and return rate measurements over sea ice. These give information on sea ice extent and type, and we believe these have the potential to aid ice chart mapping and complement data types readily available in the future. These techniques are obviously under development, and we welcome all comments, suggestions, and collaborations. Thank you very much for your attention. Our data are available through the CSDAP and EarthNet programs.
Thank you very much, Jessica. But did you have something else you wanted to show?
No, that's it. Sorry, I accidentally pressed next. I was trying to see the chat.
Sure. Thank you very much. It was very interesting. I think this type of multi-purpose measurement that you get from the GNSS satellites is really cool. Good way of getting extra information out of existing satellites. Yeah, that's interesting. I see you have a question in chat. I'll just read it out. So the question is, how much time do you need to create an Arctic-wide map? 1 hour, 1 day, or 1 week?
So because we're using lots of different satellites to all create the map, it depends quite a lot on how many satellites we've got turned on for this measurement. At the moment, we've got, I think, maybe 15 or 20. And it probably takes us, I'd say, maybe 5 days or something to get full coverage, but that depends a lot on the gridding resolution that we use for the measurements, as they're sort of point measurements rather than swaths. But if we up that with, I guess, the more interest that's shown in these measurements, the higher priority it'll be. And we've got so many satellites in orbit that hopefully we can turn on more of them and just collect all the data. It sort of depends on a few too many things, really. But at the moment, I'd say probably about 5 days to get full coverage of the Arctic.
All right. Don't see any more questions for now. Sorry?
Oh, no, I said fab. We are aiming to bring that down quite a lot. We're hoping for 1 day coverage. We just don't have that yet.
Well, I guess I will, or we should continue with the next speaker, Basad from University of Colorado, Boulder. Just can you say something?
You hear me?
Yes, and we can also
Awesome.
see your slides.
Great. Let me start sharing. Can you see the full screen now?
We can, yes.
Awesome. Thank you. Hello, everyone. My name is Behzad Vahedi. I'm a PhD student at the Department of Geography, University of Colorado Boulder. And today I'll present the preliminary results of our work on sea ice type classification using convolutional neural networks. As we've seen so far in this session, automated sea ice type classification using SAR imagery is challenging due to different reasons, including low ice type separability in SAR backscatter, the effect of surface roughness and volume scattering on ice emissivity, and shortage of machine learning oriented label data, and the SIGGRID scheme that is used for labeling the existing data. In this talk, as I said, we'll show the preliminary results of our work, highlighting the third challenge mentioned here, as well as uncertainties involved and the granularity of the labels. The data set that we used was the second version of Extreme Earth Polar Use Case Training data set. Torbjorn mentioned it briefly earlier today, and shout out to them for generating this data set. It contains sea ice analysis for 12 Sentinel-1 images in 2018. These images are 1 month apart, and the study region is northeast of Greenland, around Denmark's Haven. As I said, we learned about this data set only in September, so so far we've only used 4 images in training our models. January, February, March, and October images, and used stage of development charts as labels. The pre-processing steps that we did, first of all, we downloaded images from ESA, Sentinel-1 images, EW mode, with 400 meter resolution, sorry, 40 meter resolution. Then we applied publicly available denoising algorithm by Nansen Center to remove thermal noise. On the right, you see an example of a noisy image and a denoised image using this algorithm. Even though the amount of noise is considerably less, there is still some banding effect visible in this image, which might not be as easy to see in this small image. We then rasterized the ice charts to 2 by 2 kilometer grids which is equal to 50 by 50 pixel patches on the images, because we train our models on 50 by 50 pixel patches. And we also applied some spatial and attribute filtering on these labels, which I will talk about in more detail in the next slides. So here on the left, you see an example of the Sentinel-1 image we used for January, and in the middle and on the right, you see the corresponding stage of development charts. The image in the middle shows the oldest ice type, and the image on the right shows the second oldest ice type. And the classes that we included in this classification were 6 classes: new ice, Nile ice, young ice, first year ice, old ice, and water. But the issue is that in these ice charts, and these labels on the ice chart show the concentrations of some example polygons. Now, the issue is, if you look at this highlighted polygon, for example, which is considerably large, the primary ice type, or oldest ice type, is young ice, and the second oldest ice type is new ice. But the concentration of young ice is 1/10 or 10%, whereas the concentration for new ice is 8 to 10, 8 to 10, 8/10 to 10/10, or 80% to 100%. Now, this causes a huge issue for classification algorithms, because if we want to classify a 2 by 2 kilometer region within this polygon, which one of these types should we assign to that region? Is it the oldest type? Is it the youngest type? Is it the one with the highest concentration? So these are the challenges that this type of labeling causes for automatic classification. Now, because in this project our goal was to predict the oldest ice type, we decided to exclude samples where the concentration of the oldest ice type, or CA, was less than 50%. And we also excluded samples which were too close to the borders, and the distance threshold that we used was 1 kilometer. So with those filters involved, the samples that we got from this image, from the January image, are what you see here, and clearly we lose a lot of samples, but as I mentioned later, it sort of helps our model in the meantime. Sorry. So another result of those filters is that the imbalance problem in different ice types, which already exists in sea ice type classification, is exacerbated. As you can see in the samples that we used, both in training and testing, new ice and Nile ice each comprised less than 1% of the samples, whereas we had a lot of water samples. So to address this, we used a let me talk about the model first, and then how to address this. We used a pre-trained ResNet 50 as our model, and fine-tuned used fine-tuned dense layers at the top of it, 2 layers each with 128 nodes. And as I said, since we had 6 classes of ice, our output layer had 6 nodes. In total, we had 80,000 samples for training and 9,000 samples for testing. And we used HH, HV, and local incidence angles as the inputs for this model. And we also used focal loss, which is designed for imbalanced data sets, as well as data augmentation, to sort of alleviate the imbalance problem I mentioned before. Now, the model performance, the training accuracy was 95%, the testing accuracy was 94%, and as you can see in the confusion matrix, the model did relatively well on new ice class, even though the number of samples was very low. It also did well on first year ice and water, but not as well on young ice, and it did really did not a good job on Nile ice at all. Now, something to keep in mind here is that these values, 95% and 94%, are tested on the 10% of the samples where CA is greater than 50%. So these values are still for quote unquote pure samples of ice. To evaluate the generalizability of the model, we tested it on a completely unseen image in November. This is the Sentinel-1 image for November, and these are the true labels for oldest ice type in middle. And these are our model predictions for this image. And something to keep in mind here is that, as I said, we had trained the model on samples with concentration greater than 50%. So there are a lot of samples in this image that the model has not seen anything similar to it. But still, we got a 60% accuracy on this output. If you look at the original Sentinel-1 image and the outputs, what most probably is wind effect on this right side of the image has clearly messed up the model predictions, as well as the banding effect, which you might be able to see this band here as highly affected our result, and there's another band here which has resulted in these predictions here. Now, as I talked about it earlier, the mixed type polygons also creates an issue for evaluating our models. What I mean is that here, for example, our model has predicted new ice, and the label is young ice. But we were not sure if we have to, if the second oldest ice type here is new ice, this in fact might have been a new ice sample that our model has predicted. So in order to investigate that, what we did was we compared our model predictions not only against the oldest ice type, which is SA, but also we said, hey, let's consider if the model predicts SB, or second oldest ice type, correctly, let's consider it a correct classification, which you can see here on the right. On the right is where, when we consider both SA and SB as correct classifications, and on the left is when we only consider SA as a correct classification. And now, if you look at this, the effect of wind is still present in the predictions, and as well as banding, but the model prediction for ice classes becomes slightly better. Now, with that, I'd like to conclude my talk. As I said, we've just started this project, so it's in early stages, and we welcome collaboration. But we tried to showcase the challenges that mixed ice type polygons pose for sea ice classification. We also saw the effect of noise. Something I forgot to mention is that here in model predictions, the input image is denoised, but even so, we still see the effect of banding in the model prediction. So that's another challenge in CS classification. And the third challenge is the inherently imbalanced classes, different ice type classes, which could be addressed to some extent with different methods and different loss functions, for example, or using using data augmentation to augment the data sets. With that, I'd like to thank you for your attention. If you have any questions, you can contact myself or my advisor, Dr. Karimzadeh, using the email addresses provided here. Thank you.
Thank you, Behzad. I can see you have a question in the chat. Thank you for sharing your work on the CS classification.
Sure.
And
thank you for giving us the time. All right. Did you try other loss? Oh, sorry. It's the screen. All right. Let's see. Tora has asked if we tried other loss functions. If so, did you see a significant improvement in model performance? Yes, we've tried out-of-the-box loss functions like categorical cross entropy. We have also tried categorical cross entropy with class weights and different other loss functions. And so far, focal loss generated the best results. Off the top of my head, I don't remember the differences in terms of accuracies, but if you're interested, I can share the results with you. I think, is there any other questions, answers to me? I think that was it.
I have a question. So you showed that you used pre-trained ResNet, right? ResUnit? No, just ResNet, sorry. So the prediction of that is a single pixel, right? Does it predict multiple? Yeah.
Yeah, it's a single patch basically, because we use patches, 50 by 50 pixel patches, but yes.
Is there a particular reason you've chosen to do that instead of doing something like, let's say, a unit, or where you predict, let's say, 50 by 50 in your case?
Well, 50 by 50, we used 50 by 50 patches so that the model can see some extent, can see a spatial extent of the surrounding pixels. And we have also tried different patch sizes, out of which 50 by 50 was the best. But in terms of why we've not used units or something like that, the reason simply is because we've just started, and that's in our plan to move towards those kind of models. Yeah.
All right, thank you.
Thank you. Do I stop share? Okay. Here we go.
To unmute. Maybe we can have a small discussion afterwards, but maybe for now we should proceed to our very last presenter, Gordon from the MDA.
Oh, here. There we are. Okay. Okay, is this showing correctly? And can you hear me? Okay.
We can hear you, but you have not, we don't see the full screen yet.
There we are.
There we go. Perfect.
Okay, all right. So good evening. Thanks for having me. Thanks for staying late. And I'm going to talk about sea ice monitoring work using RadarSat-2 and deep learning. I presented some first results at ESA Phi-week last year. So the objective is to use deep learning, namely semantic segmentation, to improve or automate sea ice mapping. It's a project with the Canadian Space Agency in collaboration with the Canadian Ice Service. We have SAR data, dual pole ScanSAR wide data, labels from the Canadian Ice Service in 4 different regions of the Canadian Arctic, the Middle Arctic, Newfoundland coast, and Western Arctic and Fox Basin. So quick overview. So we have our top shows our training situation. We have our dual pole SAR data going into a deep lab semantic segmentation network. The data is normalized by the training statistics. We have our predictions and the true labels from the SIGRID charts and sample weights. So land and no data areas are assigned as 0 weights in the calculation of the loss, so the weighted cross entropy loss used to train the network. For the prediction, we have the data going in again, and the predictions from the deep lab network and a weighted metric calculation, and where we calculate accuracy and mean intersection over union. So last year we looked at ice water classification, where water was either pure water or a concentration less than or equal to 20%. Ice was greater than 20%. And one of the things we looked at last year was different training strategies. We trained separately per region, combined all the data, and then fine-tune per region. The baseline for the work here will be our separately trained strategy. And so the recap of the ice water classification results here for the different regions. Accuracies above 90%, mean intersection over union, either the high 80% or just over 90%. So the next thing we did was basically extend to use the same classification model for ice concentration. And so to do that, it just simply increased the number of classes. So instead of just ice water, it was concentration classes in steps of 20%. So either water or total concentration less than 20%, and then up to all ice or ice shelf. And as is well known, one of the limitations is the reduced amount of data available at the intermediate concentrations. These are bar charts of the fraction of pixels per class for the different regions. All the regions are pretty similar. Lots of water, more than reasonable amount of ice, and less so in the intermediate classes. These are some results. So we have our is the confusion matrix. So we have the true concentrations along the vertical axis, the predictions along the horizontal axis, the 4 confusion matrices for the 4 different regions. In each case, we have the overall accuracy for this multi-class problem and the intersection over unions for the different classes. So reasonable results for the all ice. So it goes from left to right, either all water up to all ice, and then lower intersection over unions in the intermediate classes. So in the end, this, you can see this also in the confusion matrices where there's, you know, the good bright color, high number in the ice or all water. Ideally, we'd like to see everything bright along the diagonal. But one interesting thing is often where there are errors, they're usually one class away, 120% class away, or maybe 2, except in some cases where we do a lot of make a lot of errors and predict everything as water. So I'm going to show some just image examples. So we had, so we worked on with 512 by 512 pixel chips, about 25 by 25 kilometer chips. And so to show the result, we would stitch all of these into one image, and I'll show you the HH and HV images and the label and prediction images with land and node data just superimposed for clarity, even though they're not actually classified. And you'll see, as was seen in the confusion matrices, there's some confusion in the intermediate concentration classes, usually 1 or 2 concentration classes away, where the and the ice water boundary is still represented in most cases. So this we have the Newfoundland and the mid-Arctic examples. So the HH and HV images across the top. Black is no data where there was no sea ice chart information, so we didn't have a chip there. On the bottom, we can see the labels on the left and the predictions on the right. The ice edge more or less retained, and then you can see where there's been some confusion about 1 or at most 2 classes away in both of the examples. This one here is 2 more regions, the Western Arctic and Fox Basin region. So again, HH and HV on the top, and the labels and the predictions on the bottom. Again, pretty good preservation of the ice edge, and some confusion in the adjacent classes. So the next thing that we did, so I'm back to ice water classification now, and in a problem that one of the previous speakers mentioned was the limited field of view that we have when we're looking at, we want relatively, a fine resolution for semantic segmentation. In this case, we have 50 meter by 50 meter pixels and a 512 by 512 pixel chip for about 25 kilometers. And our field of view in the Deep Lab network was about 250 pixels. So it's kind of a diagram here where we have a field of view used to classify a particular pixel by the model. But in the previous results on the ice water classification, in many of the cases in those images, you could see there was, pretty good results and good presentation, or good preservation of the ice edge. But then there were times where many parts of the scene had whole chips that were misclassified, especially in areas where there was uniform backscatter over a chip. So there was just no context within the chip for classification. So the idea is to process the image using multiple resolutions. So we use not just the original, what I call fine resolution image, in conjunction with a downsampled image. And we merge this together in the Deep Lab network so that we have, for the same size chip at a coarser image, when we first put it through a downsampled image, that's 512 by 512 chip on a downsampled image has context from a larger area, which is then carried into the fine model when we input it. So this is illustrated in this diagram here. So here's our full frame. You can see basically the size of the chip. This is a 25 by 25 kilometer what I call fine resolution chip here. And then in parallel, we downsample, average and downsample, say in this case illustrated by a factor of 2, but we'll look at a couple of different downsampling factors. And so we have the same model that we used before, but the input comes from this downsampled image. So now our 512 by 512 chip covers a larger area. You can see comparing these two chips here. And then we take the output of that, which instead of the final prediction, we just use the output of the model, which is what are sometimes called logits. So just a 2-value vector for one for each of the ice or water classes. We extract from that downsampled output, we extract the chip, which would be a smaller chip that corresponds to the fine resolution one. So if we had a downsampling factor of 2, then the chip of the downsampled output that corresponds to our fine resolution chip would be 256 by 256. So we have these matching chips input and merged in the Deep Lab model. And this becomes our multi-scale model, and we get a new prediction from that. So the results are encouraging doing this. We had, so in the Deep Lab model that we had, there were various layers with strides where we could, where it was easy to concatenate a downsampled output into that, and there were strides of 2 or 3 layers each with a stride of 2, giving us possible decimations of 2, 4, or 8. Our chip size is divisible by 2, 4, or 8, but we had a chip overlap of 100, which unfortunately is only divisible by 2 or 4. So with that, and so we did try it with downsampling factors of 2 or 4, and the best results came from the larger downsampling factor of 4. This table summarizes our accuracy and mean intersection over union for the ice water classification for the 2 regions, the Newfoundland and Mid-Arctic region. So the original single scale results across the top, and using the multi-scale with 4 times downsampling across the bottom. So we get a noticeable improvement there of at least a percent, or in most cases at least 1%. And then this is one of those difficult scenes that we had before, where so this is it's off the coast of Newfoundland. It's the HH and HV images, are the true labels, and this was our original work from last year on the ice water classification, where you can see in the middle here, there's whole chips that are being misclassified, and it looks like it corresponds to quite uniform areas of backscatter. And this is the result where we introduce the multi-scale with the 4 times downsampling. So there's the accuracy and mean intersection over union are improved significantly, and visually you can see that it does go a long way to making the result better in that case. This is another scene mid-Arctic. It didn't really look the same. It didn't have those huge areas of the uniform backscatter like the Newfoundland scene did, but Again, there was, so we have across the top the HHHV and the true labels. And along the bottom, we have the this original single scale and the multi-scale, the 4 times downsampling. Again, noticeable improvement in the measured results, the accuracy and mean intersection over union. Visually, it's not as dramatic as the Newfoundland example, but the measured results do show some improvement. And the last thing we've worked on is trying to incorporate some external weather data into the model. So we use the NCEP, or National Centers for Environmental Prediction reanalysis data, which and we chose the temperature and 2 components of wind. And it was resampled, so it's very, very coarse. I think it's like 2.5 degrees latitude or longitude. And so we resampled it to correspond to a grid corresponding to our 4 times downsampled data. Interestingly, it's a case where it didn't seem to improve overall results, but it made noticeable improvements on particular scenes. So in this case, there isn't, yeah, it's actually even slightly degraded. When we introduce this, and it could, we're just starting to look at this, so it could be in the way we've injected the data into the model. But when we look at the particular scenes, again, so we have the HH and HV, the true labels, the original predictions where there's a lot of misclassification, and the figures representing the temperature and the wind components. And for this particular scene, some improvement in the results and visually as well. So it's indicating that, yeah, there's the weather information is helping in this case. And then again, for the mid-Arctic scene, again, we have the HH and HV and the labels and the original predictions. And here is the temperature and the 2 wind components across the bottom. And again, in this particular case, noticeable improvement on this scene, and visually as well in some cases, that especially in this lower part where there's more correct classification. So in summary, then we extended our classification model to ice concentration classes, which maintain the ice water boundary, but with limited data in intermediate concentrations that affected the accuracy. This could improve with more data. We tried this idea of multiple spatial scales with the injection of output from the output of a model on 4 times downsampled data, which improved overall performance and a noticeable improvement on difficult scenes. The Newfoundland scene, which had uniform areas of backscatter the size of chips, definitely benefited from that. It's not clear yet how to best use the external weather data, which it didn't improve overall performance, but there was noticeable improvement on certain scenes. And that's it for me. Thank you.
Thank you, Gordon, for sharing your work. Very interesting with the integration of the some environmental data, which there's also happens to be a question.
Okay, let's see if I can see the chat here. Oh, okay.
Yeah, maybe Leif, I will give Leif the opportunity to do the what do you say? Ask the question orally.
Okay, here. I'm just trying to scroll through the chat here. Okay, did I resample relative to the SAR look direction? Not sure I understand it. The question: resample the winds relative. Everything was just resampled to the spacing of the SAR image. So it would have been in the ground, like the SAR direction. Yeah, in the same way that on the same projection as the SAR image itself.
Yeah, the prediction is okay, but what, did you take into account the fact that the winds relative to the SAR should be looked at in a range and azimuth direction rather than a U and V, which is north,
okay.
northeast and east?
Probably not. No, I think those are still just UV, actually. Yeah, that's true.
That might help you.
Right.
What was the resolution of the wind data?
Oh, it's about 2 degrees. So it's, or yeah, it's quite, it's what that is. It's a few, several hundred or kilometers, or it's quite coarse.
Okay, yeah.
How to do with patches next to borders where upscaled patch would go beyond. Yeah, so that was an issue. So yeah, so what happens was when we chip the downsampled data, because it's coarser, and we had a rule where there had to be at least 50% valid pixels in order to use that chip. So there were some cases where there was no downsampled chip to corresponding to that unsampled, in which case I just set the data downsample data to 0. So those border chips may not have had downsample data going into them. Let's see. They will. Okay. Oh, that's not a question to me, so I don't know. Okay, I think that's it. Maybe I should stop sharing here.
Thank you very much, Gordon, and thank you to all the presenters today. It's been a very nice session, and it's also been nice that we were able to keep the time.
Okay.
I will give the word to David, who will make a few final remarks.
Yeah, to echo Juha's sentiments, I think he's now gone, but thank you all for staying late on a Friday evening. I'm sure you all have better things to do. And also echoing that hopefully the next time we get together, it will be in person. That would be much more enjoyable. I'd just like to finish by saying there's been really great back and forth discussion in the chat. I really hope that you will all continue that. I will put in the chat a link to the discussion forum that we have set up for that purpose. I have to say it didn't get used particularly much after the last session last year, but there's been a lot more discussion this year, so hope springs eternal. We will be sending out a broadcast email to the community talking about where you can find the presentations and the recording of this, talking about, again, this discussion forum, and hopefully we can keep the conversation going. And that will be promoted by the competition. The competition has to be a bit focused because we have a training data set and we have to evaluate everybody to the same standard. So there were presentations today that aren't going to fit directly into the competition, but I hope you will consider participating nonetheless. Great. I think that's it for me. Last chance for anybody else. Do any of the other panelists want to say any last words?
There was a question from Dimitri about the registration link. I think this is in regards to the competition.
I just opened the link for the forum, and it asks login and password. There is no registration link or something. So
there should be a thing that says if to register, click here. Is there not a? There should be a registration ability. Log out. Okay. Sorry, I'm doing this. Isn't there a forgotten password? Huh. It used to be. Okay. I'll make sure somehow there's a registration link and make that happen.
Yes,
Thank
it
you
was
for
posted.
pointing that out. So I will, registration. Yeah. That registration will register you to PolarTep, which I guess now works for the PolarTep form. Sorry for the confusion. I will send out an email to everybody that clarifies all of this.
And if you could send us the presentations that you've made, that would be great. And then we can forward it to everyone.
Yeah, and if the default will be, we will distribute your presentations. If that is a problem, please let us know. But we would very much like to distribute them.
All
Good.
right. Well, thank you for today.
Yeah,
Have a nice
thank you.
evening and weekend.
Yeah, thanks. Thank you very much. I really enjoy these. Thanks.
Thank you, everyone.
Thank you for your help.
For closing the Phi week in such interesting input.